And the bachelor and master from University of Tokyo, receiving the PhD in 1996, and then get promoted, started as a research associate and went through all the paths, getting promoted to full professor and director of systems design lab at University of Tokyo. He is now a special advisor to the president of the University of Tokyo in University Corporate Relations and Semiconductor Strategies, and also science advisor of the Minister of Education, Culture, Sports, Science and Technology of Japan. He works in hardware, or works for hardware security, synchronous circuit design, smart image sensors for 3D range finding, and time domain signal processing. He has been serving various positions at conferences and journals, the senior member of IEEE, fellow of IEICE of Japan, and Vice President Membership Committee of IEEE SSCS, and also Vice President-elect of IEEE SS. This talk is sponsored by Solid State Circuit Society Egypt chapter, and the title of the talk is Acceleration of Encryption Algorithm, Elliptic Curve Pairing Post-Quantum Cryptography.
Thank you very much, and good afternoon, everyone. Thank you very much for the hosting our talk here today, and also thank you very much for kind introduction. But before going to my talk, I already introduced, but the talks are sponsored by Solid State Circuit Society Egypt chapter. So I'd like to introduce what IEEE Solid State Circuit Society is. So it's very brief, but so IEEE Solid State Circuit Society is one of the societies inside the IEEE. Working for Solid State Circuit, and we have sponsoring the 5 major conferences named ISCC, Versa Symposium, CICC, SR, and ASCC. And in addition to that, we have several, well, not several, but many conferences collaborating. Like here, and also we are co-working with many other societies like SIDA, which is EDA, or many others. We have several publications like Journal of Solid State Circuit or the Solid State Circuit Letters, Solid State Circuit magazines, and open journals, and several others co-working with other societies. So what SSCS is working for? So basically, we have been providing very rich educational materials inside, and on top of that, we have the almost 160 chapters worldwide, one of which is this Egyptian society. And we have many archives of tutorials and talks on our SSCS website. So if you have a chance, please go there to see some of them. And of course, on top of that, you are welcome to join the SSCS Society members. And we have been sponsoring many activities like a PICO Open Silicon Design Project or Circuit Insight for undergraduate in many major conferences. Or we have the Student Design Contest or Arduino Design Contest or some others. And we are also working to encourage such kind of activities. So if you are really interested in, and especially those who are interested in working for the student branches for SSCS, you are welcome. And Nagata Sensei and I are also working to encourage that kind of thing. So if you are interested in, please let us know during or after this talk. Okay, so let's going back to the main topic here. So I'm not quite sure that you are not aware of the security. Basically, in your daily lives, at least you're working with security. For example, if you log into your server, if you use your mobile phone, at least they have the password required, and that means you are using security. But on the other side, if you are requested to use security, then maybe many of you are hesitant to adapt that. So that is some nature of security. But they are, because security is something like an overhead to everything. So how we can relax such kind of overhead and to fully benefit the security feature is most important portion of the security. So to help that, one of the important things is to accelerating those kind of security functionality so that you can use them without the much overhead in time or any other cost manners. So that's the reason the acceleration of the crypto algorithm will be one of the important portions. By the way, we got several very good national grant for security. One of the reasons was that you might recall that we had a Tokyo Olympic game in 2020 originally, but moved to 2021. And once that Japanese government are keen about the security. So they put a certain amount of money to security. At the beginning, that was only the cyber security. But soon after that, they decided to put also to the hardware. Because hardware is a sort of the source of the security or the trust. So anyway, from that until now, we are working with the governmental project for enhancing the security. So I myself, along with the Nagata sensei, working towards that kind of the project. So maybe, of course, many of you know the crypto algorithm like the AES for encrypting data, or some of the digital signature authentications, and so on and so forth. AES is the major the crypto algorithm nowadays. Many people are using, but it's a bit boring to me, so let me start with the elliptic based encryption, and then some sort of functionality about the encryption. And then I'll talk about the recent activity named post-quantum crypto algorithm and those accelerators. So by the way, of course, I expect everyone knows the encryption or the digital authentication, but how many of you know the functionality over the crypto algorithm? Do you know some of them? Oh, you know. Good. Good. So basically, the functionality means the many meaning, but there are many functionality can be realized over the cyberspace. One of which is attribute-based encryption. So, as I mentioned at the beginning, if you are working with the, say, crypto algorithm or encrypting something, you need to have a password to encrypt or decrypt your data. But once your password revealed to the outside or the others, encrypted data will be no more secure. So, of course, the important thing is how you protect the password. But anyway, there are the many chances that the password will be broken or revealed to the outside. Instead, if you can realize such kind of functionality without using explicit password, that means the password is implicitly they are generated and you use for encrypting data or decrypting data. Then, because there are no explicit password existing, So that makes a much safer situation than using the explicit password. That is the attribute-based encryption or attribute, I don't know. Yes. The signature generation. And also, there are several others, like searchable encryption, that of course, if you put your data onto the cloud services, you may encrypt the data, that the data will not be stolen or not be observed by the cloud services. But if you want to utilize those data, at least at this moment, you have to decrypt your data and you have to utilize them. Well, if the cloud service provider is something, well, not the secure person, they might try to steal your data. Of course, we expect that kind of thing won't happen, but still we need to be afraid of that, especially if you are coping with very secure data. For example, if you're working in a hospital and you need to work with the card of the patient, those kind of personal information is very, very important. But from time to time, you have to extract the statistical data. How many cases of this symptom existing at this moment? Or is that increasing? Or is that decreasing? Or something. So for that purposes, we need to ask doctors to extract the statistical data at this moment. It's not efficient at all. But if we can realize that kind of thing in cyberspace, without exposing the personal data, that would be beneficial drastically, without sacrificing the personal secure data. So that kind of thing can be realized by searchable encryption. So and the others are also existing, and to realize this kind of functionality, we have some sort of mathematics existing. So, but at this moment, those kind of the computational complexity is very high. So it's even utilizing by supercomputers, it takes too much time to realize. But if you can accelerate that kind of mathematics by hardware, that could realize in daily lives without such a timing overhead. So that is our expectation, and on top of that, we call homomorphic encryption. That any kind of the operations can be done in cyberspace. Operation means something like a mathematical operation like addition or multiplication, or any kind of logical operation like doing AND or any kind of operations. So that means this is the far end of this kind of functional encryption, but we can do any kind of operations over cyberspace, so that you can modify the data, you can do sort of the computation inside the cyberspace, and so on and so forth. Of course, this requires much the heavy computational the cost. So, but if you can realize this kind of functionality, this helps to preserve your secure data much better than the current situation. So this could be the sort of the final target for functional encryption. And then what is happening right now? So you know that this is the year of 100th anniversary of quantum. You know, so the first fundamental physics they revealed in 1925. So many people are celebrating that, and one of the very important outcomes is the quantum computers. And the quantum computer having the very capable thing for the factoring, solving the factoring. And the factoring is also the security of most of the major cryptoalgorithms like AES and RSA and so on and so forth. So because of that, if the quantum computer progress drastically, then the current crypto algorithm will be broken by quantum computer very easy. Of course, I'm not questioning that will happen tomorrow or next year or 10 years later. Because the number of quantum qubit required is something like a few thousand. Even they operate correctly from the beginning until they solve the problem. I don't know, at this moment, the Google is now announcing around the 1,000 qubit will be the emerging in short. But I don't know whether it will be really they go up to such kind of number of qubit with error-free manners. Anyway, the important thing is if your data is just for the few years, it may be okay. But for the case of this kind of thing, the passport, maybe passport lasts 10 years. Then do you think this data can be secure for next 10 years, even with the progress of quantum computers? Or maybe you should have the social security numbers existing. Do you think the social security should be last for more than 30 years, maybe for your case 50 years from now because you are very young? Then do you think your data can be secure for next 50 years? Nobody can guarantee that. So because of that, we need to cope with even the quantum computer will be progress. We need to secure that kind of data. So because of that, the U.S. government or the institution NIST is announcing post-quantum crypto algorithm, and the three of them have been listed as the standard, and there are many others still under discussion for the next candidates. So this is again the very important direction to preserve our secure information. And of course, the computational complexity is also very high. So we need to accelerate them by hardware acceleration. So this is the idea that why we need to accelerate these kind of crypto algorithms. And on top of that, they are all digital algorithms. So if we can implement that in some hardware, then we can speed up using the advanced process technology, like going down to FinFET or get all around or something. So that is another benefit. But I should mention one more thing. So as I mentioned, this is the 100th anniversary of quantum. But at the same time, this is the 100-year anniversary of FET, field effective transistors. So the first patent was filed in 1925, and the date was October, I think the 17th or something. So this is 100-year anniversary FET. FET means the basis of all the ICs at this moment. So several years ago, you may recall that we celebrated the 75-year anniversary of transistor, which was invented around the year 1947. But that transistor was sort of the pin junction, the connected junction transistors, which is nothing to do with current field effect transistors. So that's the reason this year is much more important than the transistor invention of transistors. Anyway, so let's get on to the hardware accelerator design operations. So we borrow this one from the website or mathematicians. So basically, if you see this kind of list of the equations, if you are working with software, the best one should be this one. No one will use this one. On the other side, if you're working for the hardware, and if you have the 4-stage pipeline functional unit. Then what happens? Because this one having a strong data dependency, so case 1 and case 2 having the same computation time. Of course, case 3 having a bit longer than those two. So what is your choice? You may use case 1 or case 2, maybe, but it's not, because this is security. So as I mentioned, if some of the information revealed related to the secure information, that might cause the serious issue. Well, Naga-sensei will coping with how to attack this kind of hardware. So he's my enemy. But anyway, but finding the such kind of the problem is very important for hardware security. So for this case, we found that the completion time of the adding operation and the doubling operation, we need to have those two, and we need to pick one of them at the end. It's something like this. So unfortunately, this one having the data dependency, so we cannot move this one until the end. This is the same. Fortunately, this one can shift towards the end. So because of this nature, we cannot use these two, although this having the shortest completion time. We need to use this one for the security issue. So this is another important aspect for the hardware, the accelerator for Cryptoalgorithm. If you are working just accelerating some of the different algorithms, that's fine. You can use case 1 or case 2. But for security reason, we need to use this one. For example, this is a very simple example, but this is a very important aspect for the hardware security. Then what else? As I mentioned, we have a freedom of the world side of the function unit. For example, this is the case for the elliptic based cryptoalgorithm using 256-bit keys. We have a choice using 256-bit keys, the data size, the world size for the entire function unit. We can use 128-bit, 64, or else. Of course, if you use 256-bit, this is the axis of the hardware size. This is the axis of computation time. So we can realize very fast one with huge hardware. That's good. If you can reduce down to 128, the area go down to almost half. The time go up about 2 times. Going down to 64, again area go down half, and the time go up again almost twice. But after that, if you go down to 32-bit, area reduction is very small. Or if you go down further, smaller one, you cannot no more see the area reduction, but only the increase of the completion time, execution time. What is the reason behind that? Because for any cases, we need to have intermediate memories to store 256-bit the data. So memory causes the area, the reduction saturations. So for these cases, either these three is optimal. And below the 32-bit, the data bus is almost useless. Of course, except if we can utilize SRAM, then of course SRAM having the memory access time issues, but still we can reduce the entire hardware size drastically. Because as I mentioned, they are limited by the memory size of the intermediate data, which is realized in crypto because of the accessibility of data. So we have implemented with the same 65 nanometer process technologies for very big, fast one, and very small one with using SRAM. So what was the result? Of course, as you expect, this one exhibit very fast operation, like 30 microsecond operation for single crypto operation or pairing the operations, but consuming almost 1 watt. So some of you might have the idea that currently the Intel microprocessor consumes about, I don't know, 30 watt to say 100 watt, with almost billions of transistors or billions of gates. For this case, this is only 1.5 million gates, but consumes almost 1 watt. This is because we optimized our hardware, so the almost all the, or I should say, 80 to 90% of hardware is operating for all the time. So that's the reason that the power consumption, according to the number of gates, are huge. But because of that, the power efficiency is very high. So the minimum energy, if you reduce the operating voltage down to say the 0.4 volt, becomes something like a few femtojoule per operation. For the case of this very small one with SRAM, of course, as expected, it is very slow in operation, like 1 millisecond of operations. But that they demonstrate almost the less than 1 milliwatt of the power consumption. So that's a huge difference, 1 watt down to less than 1 milliwatt. But if you go down to the energy minimum point, that consumes about 100 femtojoule. So the energy efficiency is much higher for this case than this smaller one. Because this is very small, very slow. So that results in the huge amount of the leakage power consumed for the low voltage operation for this case. Because the hardware efficiency is not high for this case. So this is what we learned. And anyway, we have designed the two extreme cases, like a very slow one with very small gate size and very fast operation with very huge amount of hardware resources. And as I introduced here, we could design any kind of hardware if you have any target or specification, like the number of gates or the performance requirement. We can design for you with this kind of trade-off data. So this is what we have demonstrated for the elliptic based crypto algorithm. And what's next? As I mentioned, functionality is one step above the security, and the pairing operation, which realizing this kind of bilinearity mathematics, is one of the bases for such kind of functionality. So I'm not going to the detail about the mathematics, but important thing is at this moment or in the past when we started this one, this performance requirement was two order of magnitude faster than at the prior state of the art. To realize the functionality like a searchable encryption in real time. So the two order of magnitude, the performance improvement was some sort of the target at that time. But what is the pairing operation of bilinearity? Pairing operation is defined in the extended field. As I mentioned, the elliptic guide is defined in the primary field, or the primary number field. Extended field is something like from the real number to the complex number. adding the dimensions. So for the case of the one of the pairing friendly curve utilizing 12 extended fields, that means we having the 12 degrees space. It's expanding like this kind of equations. So we can expand 12 extended field number from this one down to the primary field, the mathematics, or any kind of intermediate dimension can be utilized. So what should be the optimum? We explored the things and identified that using the secondary extended field as a main function with the constant multiplier and primary field multiplier as a sub-functions. So with this, and also the number of pipeline stages we need to utilize would be 12 stage pipeline. We have the intensive work for the what will be the best and doing the scheduling, and they realize this kind of hardware. For this case, the number of gates are something like 3 million. And one pairing requires about 30 microseconds. So as I mentioned here, I skipped, but at the prior time, the execution was something like 10 times larger than the elliptic-based operations. Or I should say computational complexity is 10 times higher than the ordinary elliptic-based operations. The result we obtain, the time required using the same CMOS process is just the same as the elliptic-based operations. It is almost as equivalent 30 microseconds. Why it is? Because pairing having much the algorithm level parallelism existing. So we can fully utilize the hardware parallelism to enhance the performance. Of course, for this case, with the 3 million gates, they consume about 3 watts. That is almost much larger than the elliptic curve, and also much larger power density than the ordinary microprocessors. So, as I mentioned, we could realize 1 order of magnitude performance improvement in the prior comparing with the prior art. What else we can do? Of course, from 65, if we go down to 12 nano FinFET, this gives you the performance improvement. For this case, I'm not quite sure this is the best optimal result, but we could go down to 10 microsecond operation. We could expect that if we go down to 2 nano or 3 nano, then we can reduce improve the performance, maybe 10 times or something. So that means we can realize the 2 order of magnitude, the performance improvement. That is the advantage using the fully digital implementation. For the fully digital implementation, we can obtain the full advantage using the advanced process technologies. Of course, there are some other things we can do. For example, for the case of searchable encryption, we often use so-called multi-pairing operations that require this kind of the multiple pairing for single data. So for that, we can use the multi-core implementation for the same pairing engine. That improves further the parallelism or the hardware accelerators. So we have tried such kind of things and obtained the further improvement for the pairing operations. Or we have demonstrated the performance improvement by the process technology improvement. So with this kind of thing, we can fulfill the sort of the requirement to realize the functionality in reality. So we have demonstrated this kind of thing. This is our design chip, and we connected our chip to the CPU, and demonstrated the searchable encryption running on the software, and diverting the pairing operation onto the hardware, demonstrating the performance improvement. So what else we need to do for this? So for the case of pairing operation, different from elliptic based encryption, there are no standard existing. If you're working for elliptic then there are many kind of standards existing. So depending on your requirement on the standard, you can choose the curve parameters. But because there are no standard for pairing curve parameters, so the choice of the curve parameter is the biggest interest. Of course, we can choose the curve parameter depending on the security level we require, or the software that the people are using, and so on and so forth. At the beginning, we utilized this named BN 254-bit curve as our example. At that time, the people mentioned, oh, they maintain the good enough or enough security. But for a few years later, people mentioned that security is degraded down to 100 bit to 110 bit. It's no more secure. So we are so upset. So what kind of the parameter we should utilize for secure ban? We didn't know. We investigated several others, and but we didn't know actually which one should be the best optimal. So to extract such kind of thing, instead of designing entire hardware and showing the performance and security level, we need to have sort of the estimation from the curve parameter or parameter equation to the hardware. So we have the real sort of the design automation by template-based design. So from the curve parameter described here or exampled here, we extracted the list of equations and we applied to the templated hardware by the scheduling and obtain the result. So this is the sample of the template for each curve. And doing this kind of scheduling, although this is not so efficient the scheduling at all, but then we could realize this kind of almost fully packed the scheduling and obtaining the results. Of course, this means the template-based design, and this one is the handmade design. So if we see the details, the performance is twice as large because we haven't put specialized the hardware to optimize the data bus, but because of the gate sizes are slightly smaller than the strat design. But for most of the cases, the ratio from the handmade design and automated design is something like 1 to 2. So with this, we can somehow guess the expected result. And on the other side, the security level can be identified by this kind of the equations. So with this, we can plot the curve parameters from the security level and require the hard latency or hardware size and so forth. With this, if you require only 128-bit security level, then this red curve, meaning the BS12 curve, would be the best for the case of latency. area might not so change. But for the functionality, we may require excess the security level. So for the case to maintain entire security level to 128 bit, then we sometimes require 150 or 160 bit security. Then that means we need to choose something like here. Still, the BS12 gives you the faster operation. But area-wise, BS12 is much larger than BS24. So this is your choice, that whether you use the BS12 or BS24. Whether you put emphasis on the performance or hardware size. So that is what we learned from the trial. Then, at the end, let's move on to post-quantum design examples. So, unfortunately, this is still ongoing, and they show some of our latest examples, and there are several types of post-quantum cryptoalgorithm existing. One of the major one is lattice-based one, and of course there are another one code-based or hash-based or polynomial-based and isogeny-based existing. So let me start with the lattice-based one. Lattice-based one is something like the matrix operation, but adding this kind of error term. What does this mean? Or error means the random number. With introduction of this error number, quantum computer cannot solve this kind of equation at all. But for the ordinary computer, we can realize, you may know that the root mean square type operations to the abbreviate or the number. So with using the same, almost same kind of very large matrix, this will be tolerant to the quantum computers, and also this is very tough for ordinary computers. That is the source of security of this lattice-based post-quantum algorithm. So basically, the basis of basic operation is this kind of the matrix operation. To accelerate this operation, there are only one type of acceleration existing, which is called NTT, numerical transformation theorem, which is just the same as FFT type operation. That if you want to realize this kind of method of operation, you need to require n square the number of operations. But the NTT reduces them down to n log n. So that is the only way we can accelerate that. And these are the steps for the key encapsulation algorithm, which is key generation, encrypting the key or decrypting the key. Basis again and again this kind of matrix operation. And because of that, we need to use NTT to accelerate that. But that is not only the required operation. We need to have hash function, and we need to have several other the mathematics required to realize. So anyway, at the beginning, we just focus on the NTT portion, how we can accelerate the NTT. So as I mentioned, NTT is something like this kind of butterfly-like operation in FFT. And so there are many techniques existing to accelerate this one. The problem is if we increase the number of the butterflies, we need to increase the memory access bandwidth. So this is something like a trade-off between the performance and the memory access. So we need to seriously think about such kind of optimization to realize the best optimal result. But it was not only this one. For the case of the newly introduced SHA-3 hash functions, again and again, this is relatively heavy hash function than the previous SHA-256 or SHA-2 operations. So at first, we try to implement the best optimal design for crystal time one security level, the operations. Of course, we could successfully realize the process operation at that time, but we haven't the optimized entire data flow. Instead, as I mentioned, NTT is something. We have hash function here. We have several other functionality to finally complete entire the KIM operations for digital signature authentication operations. So optimizing everything aligning will be was a very important portion to optimize the entire data process. So at this moment we have intensively working for that, and some of the result is something like shown here. So basically we already could realize all the security level defined in the NIST standard or the fifth standard, and we could realize the process operation, the number of clock cycles comparing with the state-of-the-art results. Some of the cases we could realize more than 4 times faster operations. That's the same for KEM, and we have demonstrated process operations like this. Comparing with the others, we realized almost order of magnitude faster, except this one. This one is our first trial, just focusing on this security level. This one could not realize the other security level. So with this, we have demonstrated fastest operations. The question is, as I mentioned in the elliptic curve, we are now seeking what is the minimum available the hardware that could realize the similar functionality to demonstrate the sort of the design spaces. So we are still working towards that. Of course, I'd like to introduce many others, but one of the unique one is called isogeny. Isogeny is something like the mapping function between 2 curves listed here. So this is the pair of the elliptic curve, and the isogeny is starting from the point over one curve, finding the so-called kernel point on the other curve. The way to find the point is something like a random walking, like this, in between those 2 curves. Of course, the one of the proposals named sign have been broken by the ordinary computer, not by the quantum computer. So it is regarded not usable for the post-quantum, but still many people working to investigate the further, the safer the algorithm over the isogeny operations. But anyway, the isogeny is corresponding to 3 operations, one of which is point doubling over an elliptic curve, like red arrow shown here. The other one is mapping, point mapping from one curve to the other. And the last one is getting the point mapping functionality calling the kernel function. So mathematics are something like this. So the point doubling is just explained at the beginning of my talk. Point mapping is something explained like this mathematics. Kernel operation is something like this. So basically, with this one, we could optimize our hardware, but the complexity is far larger than the ordinary elliptic curve. Because, as I mentioned, this is a random walking. So starting from this point, finding also the last point here is the isogeny operation. So for that, we need to have this kind of random walking or that kind of random walking. Which one is best? So that could be identified by this point doubling operation that requires a computational rich operation, and mapping, which requires memory storage for these points. And with those kind of the cost functions, we could obtain the best passes to realize this. For this case, this pass 2 is the better than the pass 1. So with that, we should identify the best optimal path for the hardware we implement, or the cost that required for each operation. So what we can do, it's no cycle, as I mentioned, but there are many other complicated algorithms existing or proposing. One of which is called QFESTA, which utilizing two isogeny means two sets of the curve required, and that require almost 1 second of operation for single isogeny operation. So this could be the good target to accelerating by hardware. So we are now designing using this kind of template, which is almost equivalent to the template that I introduced in the pairing operation. And we have demonstrated it onto the FPGA, and even with the FPGA, comparing with the CPUs, it could accelerate almost 8 times. So we are expecting if we map onto the ASIC, we could be accelerated by 1 or 1.5 order of magnitude faster operations. So with this, I'd like to conclude my talk. So basically, as I mentioned at the beginning, so Cryptoalgorithm is the pure digital algorithm. So basically, once we describe that one onto one hardware, then we can migrate to the advanced process for obtaining better performance in terms of speed. Also, we can reduce the power consumption and so on and so forth. For the functionality, we can use the pairing, which is the much complicated algorithm. But with that acceleration, we can realize functionality in real time. And of course, nowadays, post-quantum algorithm should be the very important focus. And we have still many things to accelerate those algorithms. So that is all I have today, and I'm happy to take any kind of question. Thank you very much for your time.
I wanted to ask whether is everything mentioned here is still in a research phase, or is it implemented actually in the hardware? Or
okay, that's a good question. So for the case of isogeny, unfortunately, because the hardware is very complicated, so it's not really directly going to the ASIC. And instead, we, to risk the bugs. So because of that, we use FPGA to sort of doing checking. But of course, the other example that I demonstrated here, like this is real hardware I implement onto the ASIC. And this one have been already demonstrated in real chip. This one is still ongoing for fabrication, so we are now fabricating this one. And all the others demonstrated here. Like this one is a real chip. It's not a FPGA, but real chip. So they're showing like this.
so some are actually implemented depending on the resources needed, or some of them are implemented, and the others that need more resources are not implemented yet.
That's correct. Yes.
Okay, I have another question in the slides, like not at the end of the slides, at the beginning when we were talking about 3 cases. I didn't understand why the third case was better, although the time ended. Was it because of, I understand that case 1 and 2, for example, had the same time because of pipelining, and the interdependency, but I didn't understand why case 3 was better than both of them.
Because for the case of data implementation, the choosing either the adding result or doubling result is the important choice, and that depends on the K. K might include the secret information. So if you are going to see this one, then the result here will be right one in this timing.
Would be what?
Result of the adding is right one at this point. On the other side, the result of the doubling is right one here. So if you need to choose either of these one, if you are going to choose this one, then there are no write back here. Writing back to the memory causes the bit larger power consumption than the other operation. So that means if we have the power consumption here or here, you will identify whether this was a K equals 0 or 1. So because of that, this reveals the timing, so-called timing information to the outside. But for this case, because we can move this one, because we don't have any data dependency or the hardware limitations, because this cannot shift it to the end because of the hardware limitation and the data dependency, but we don't have this one. So we can move this one to the end. Then the timing of the completion.
So we need them to be closer together, the adding and the doubling? I understand nothing.
Thank you very much for the nice talk. You've mentioned that the post-quantum cryptography algorithms have the upper hand, like because of the additional error or the random number that you mentioned is going to be added. So aren't even random number generators vulnerable to quantum computing attacks, like whether it's a pseudo random number generator or a quantum number generator?
Yeah, that's very good question. So basically, you're right. So randomness of the random number generator is one of the important factors for keeping the security. But at least if you go into the list or FIPS, the standard, they have the guideline for random numbers, but that is not so strict. One of the reasons is the randomness introduced here. If this is random, that's fine. Because of course, if the randomness is somehow too much distorted, then that might be causing the vulnerability for the security. But other than that, if you keep the sort of randomness, the number itself is not very important. So if you are talking about real number with a random number generator, which is like a pseudo random number generator like a LSA bar, then that causes the serious leakage for the data, if the data itself is important. But this is just an error. So number itself is not so serious issue. So that's the reason, and also because we're not seriously working for random number generators. Of course, many people are working for us. So we are just seeking or borrowing that kind of result. So random number generator could be off-chip, either off-chip beside our accelerator. Of course, to give you easy access, if we of course put the random number generator like a LSFR type the random number generator on chip. But we can skip that one and we introduce the random number from off chip for the keeping the security. So of course random number is very important, but it's not so serious than the random number. as just like a secret key or something.
So basically, the invulnerability comes from the classical algorithm itself and not from the random number that it's generated.
That is my understanding, yes.
Okay, thank you very much.
Other questions? Let me thank you. Yeah.
Hi, sorry. So I'm just asking, so the work you've done is just focusing on implementing the actual algorithm, but in a more efficient way. Either if we are concerned with mainly the time complexity of the operation. The thing I didn't understand whether we are focused on the power consumption part, if we are just lowering the power consumption of the computation, or we are more interested in lowering the cost of realizing the algorithm.
Okay, that's a bit tough to answer. So, one thing I can demonstrate is that power density is high because we implemented like this, all the functionalities almost being used all the time. So that is the one thing that the power density is very high. So because of that, it's not so easy to say that the demonstrate or the estimate power consumption at the beginning of design. For example, if you are using the logic synthesis for your circuit design, then logic synthesizer will give you the estimation of power consumption. But for this case, because this is too dense, so their estimation is nothing true. So because of that, we haven't targeting the power consumption as our primary design target. Instead, we just focusing on performance and the number of gates. And at the end, after we implement everything, we can of course extract or estimate the expected power consumption for that design. And of course, at the end, we of course doing this kind of measurement for real power consumption. So that is part we are doing at this moment because the power estimation by logic synthesizer or something is nothing true because this is the far extreme than the ordinary logic design.
So we are focusing on the time consumption and regardless of the power consumption.
That's right. The power consumption comes at the end.
Yeah, and using the most of the hardware we have implemented on the chip.
Yes, that's right. So we really focusing on the hardware efficiency to minimize the performance.
Okay, thank you.
More time for more questions? Okay.
Yeah.
Thank you.
Thank you very much.
Thank you. So let us have a 10-minute break.